Have you ever stopped to actually think about the invisible strings holding, well, our entire universe together? I'm talking about that relentless, unseen pull that keeps our feet planted firmly on the ground, drags entire oceans across the globe, and literally orchestrates the cosmic dance of the planets. Welcome to this explainer on gravitation. Today we're going totally micro to macro to break down the exact mechanics of this absolutely fascinating force. So our story kicks off with one of the greatest historical detective stories in all of physics. You know the legend, right? Sir Isaac Newton sits under a tree, sees an apple fall, boom, eureka moment. But here's the thing. The real genius wasn't just realizing the Earth pulled the apple down. No, the breakthrough was Newton looking past that tree up at the moon and asking a totally profound question. If the Earth is pulling the apple down, is it pulling the moon too? And if it is, why on earth doesn't the moon just fall straight down exactly like the apple? Okay, let's dive right into this and break the mechanics down into 5 crucial chapters. 1. The universal pull. 2. Unlocking planetary motion. 3. Gravity's earthly quirks. 4. Mass, weight, and tides. And finally, Chapter 5. Free fall and escaping. All right, starting off with Chapter 1. The universal pull. You know, we tend to think of gravity as just a planet thing or a star thing. But according to the source material, gravitational force acts between absolutely every single object in the universe. If it has mass, it pulls. Simple as that. Newton formalized this with his universal law of gravitation, which is beautifully captured in the formula F equals G times m1 times m2, all divided by d squared. Let's quickly demystify this. The force of attraction is directly proportional to the masses of the two objects. So bigger masses mean a stronger pull. But check out the bottom of that fraction, d squared. This is the famous inverse square law. It means the force weakens dramatically with distance. If you just double the distance between two objects, the gravitational force doesn't just cut in half, it actually drops by a factor of 4. It's a huge drop-off. To put this into a really relatable daily context, let's look at a fascinating mathematical fact derived from our sources. Imagine 2 friends sitting on a park bench, exactly 1 meter apart. Let's say one weighs 75 kilograms, the other 80 kilograms. Because they both have mass, they're actively pulling on each other gravitationally right then and there. But if we run Newton's formula, that force is exactly 4.002 times 10 to the negative 7 newtons. That is a microscopic, almost completely imperceptible force. It's totally overpowered by the friction of the bench they're sitting on, which is exactly why we don't uncontrollably slide into each other when we take a seat on the bus. Moving right along to Chapter 2, Unlocking Planetary Motion. Now, scaling up from that park bench to the entire solar system, to figure out how gravity commands the planets, Newton actually had to stand on the shoulders of another absolute genius, Johannes Kepler. Kepler meticulously tracked the planets moving across the night sky. So long before Newton had the math, Kepler had the raw observational data. He compiled this massive mountain of data into 3 distinct laws of planetary motion. First, he realized orbits aren't these perfect circles we always picture. They're actually ellipses. Second, planets move way faster when they get closer to the sun, sweeping out equal areas of their orbit in equal times. And third, he found this precise mathematical relationship between a planet's distance from the sun and the time it takes to complete one full orbit. So Kepler really figured out the what of planetary motion, but it was Newton who eventually swooped in and provided the why using gravity. Now what's really interesting here is how Kepler's first law actually looks in practice. Notice the shape of the orbit. It's an ellipse, kind of like a squished or stretched out circle. And pay attention to where the sun is sitting. It is not dead center. Not at all. It sits at one very specific focal point of the ellipse. This geometric reality is absolutely crucial to understanding why gravitational pull constantly varies slightly as a planet travels along its path. But wait, why do planets orbit at all instead of just, flying off into deep space? That brings us to centripetal force. In physics, centripetal literally translates to center seeking. For any object to move in a circular or curved path, there has to be a constant inward pull dragging it away from its natural instinct, because its inertia just wants it to fly perfectly straight. Think of it like this. Imagine a girl tying a stone to a piece of string and spinning it around her head. Her hand is actively pulling that string inward, constantly forcing the stone to turn and stay locked in that circle. If she lets go, boom, the inward force vanishes, and the stone flies off in a straight line right tangent to the circle. Gravity is basically the invisible string of the universe. The Earth provides that exact same constant inward centripetal force on the moon, keeping it forever turning in its orbit instead of just flying away into the void. let's bring things back home with Chapter 3, Gravity's Earthly Quirks. So there's this super common misconception that Earth's gravitational pull is just this single, unchanging number no matter where you go on the planet. But let's actually look at the data. The acceleration due to gravity, which physicists call little g, is heavily dependent on exactly how far you are from the center of the Earth. At sea level, g sits at about 9.8 meters per second squared. Climb all the way up Mount Everest, and surprisingly, it barely changes at all, still 9.8. But launch a weather satellite 400 kilometers up, gravity weakens down to 8.7. Go all the way out to a communication satellite at an altitude of 35,700 kilometers, and little g completely plummets to just 0.225. Thanks to that inverse square law we looked at earlier, the further out you go, the dramatically weaker Earth's grip becomes. Which leads us perfectly into Chapter 4, Mass, Weight, and Tides. Now, in our daily lives, we use the words mass and weight interchangeably, like they mean the exact same thing. But in the world of physics, mixing these two up is a total cardinal sin. So the crucial point is this. Mass is the actual amount of matter present inside an object. It's a scalar quantity. If you have 75 kilograms of mass right here on Earth, you're going to have 75 kilograms of mass on Mars, or even if you're floating out in deep space. It literally never changes. Weight, on the other hand, is a force. It's the measure of how hard gravity is actively pulling on that mass. Because gravity changes depending on your location, just like we saw with those satellites, your weight actually changes too. You quite literally weigh less standing on top of a mountain than you do down in a valley, even though your mass is exactly the same. How wild is that? And this brilliantly illustrates how these gravitational forces operate on a massive planetary scale between the Earth and the Moon. The Moon's gravitational pull isn't just some abstract math concept. It physically drags the liquid oceans of our planet. The water directly facing the Moon gets pulled outward, creating a high tide. And the math behind this is so incredibly precise that we can perfectly predict exactly when and where the sea levels will rise and fall every single day, entirely based on where the Moon is in its orbit. Finally, we arrive at Chapter 5, Free Fall and Escaping. Let's look at the absolute extremes of gravitational mechanics here. Falling perfectly and escaping completely. When you drop an object and gravity is the absolute only force acting on it, it's said to be in free fall. In a completely perfect free fall, the object starts with zero velocity and accelerates downward uniformly at that rate of g. But here on Earth, true free fall is incredibly rare because, well, we have an atmosphere. Air resistance creates friction, which pushes back against the falling object. Therefore, as our sources point out, true freefall only really happens in a complete vacuum, where gravity has absolutely zero competition. But what if you don't want to fall at all? What if your goal is to leave entirely? Well, that requires overpowering Earth's gravity. To escape Earth's gravitational field forever and not get yanked back down, an object has to be launched upward with a mind-bogglingly high initial speed. For Earth, that magic number is 11.2 kilometers per second. Yep. That is the escape velocity. Any spacecraft headed out into deep space has to break this exact speed limit to sever that invisible string for good. Which actually brings up a super fascinating question that tricks a lot of people. When we see astronauts floating around in the International Space Station, we naturally just assume they're in zero gravity. But wait, remember our table from earlier? At their altitude, gravity is still pulling at about 89% of its strength on the surface. So why on Earth are they floating? Well, here's the secret. It's because they're in a constant state of free fall. They are falling toward Earth, but the space station is moving horizontally so incredibly fast that the curve of their fall exactly matches the curve of the Earth itself. They're basically constantly falling and just constantly missing the ground. That endless free fall is exactly what creates the crazy illusion of weightlessness. It's just incredible to think that all these laws, mapped out by Kepler and Newton centuries ago, still totally dictate our universe today. But as we know, science is never truly finished. In 1916, Albert Einstein predicted something even wilder: gravitational waves. He theorized that massive cosmic events actually create these invisible ripples that alter the very fabric of space-time itself. And crazy enough, exactly 100 years later, using hypersensitive instruments, scientists finally detected them, cracking open an entirely new frontier in physics. So the next time you drop your keys and watch them at the floor, ask yourself, what other invisible waves are passing right through you at this exact second?